games so that you can publish your, yeah. Is it useful for that? Or do you have other tools?
Yeah, I like that. I tried using like NVIDIA's Basic tool,
Mm-hmm.
and I found that the stream was like really choppy.
Hmm. That is surprising.
Yeah, I thought so too.
You would think that NVIDIA knows how to utilize their own hardware, to kind of maintain the quality of the video without taxing the processor much. Interesting.
It was just the live streaming that was like that
Hmm.
had a problem. Like the game capture for like video was fine,
Hmm.
but if you tried to make it live to YouTube, it just
Oh, that could be the networking part or the encoder to stream to YouTube.
yeah.
Okay, good to know. Yeah, OBS is kind of neat because it also shows you cannot see it because it's off the screen. It also shows how much processing power it is using on this computer to do all the encoding. And right now it's using about 6%. It peaks at about 6.5%. So it's not using a whole lot of processing resources from the main processor's perspective. It's good to keep an eye on that, because this is a relatively new computer. On my older computer, the really clunky tank, laptop computer. Some of you have seen that. With that one, it will take up to like 30-40% of the processing resources, just because the processor is much older compared to this one.
Looks like a briefcase.
Yes,
Looks like a briefcase.
and it is a blunt weapon too. You can throw that thing, hit someone, and the laptop will survive. Not sure about the person. And I'm pretty sure it can stop, certain fast-moving projectiles as well. So you can use it for defense. All right. So we're getting back to binary subtraction, and if you kind of watched the video from last Thursday, you will know that we just talked about the overall equation and how we can use a or instead of an addition when we talk about how to combine the two places where a borrow can happen. Okay, so let me first open up the slide and get rid of that. I'm just going to get rid of all the other stuff that I don't need because that makes it hard to find what I need. Okay, so we are talking about binary subtraction, which is this particular module. And the discussion ended with me proving to you that a OR can be used in place of an add. So let's see. So right here. Okay. So we get to this equation. It is very much like the equation for determining ki plus 1 in the case of an adder. Okay. So there are two reasons why we end up with a borrow of 1. Two potential reasons. One is because the given numbers or the digits of the given number has a 0 for x and a 1 for y. That kind of makes sense, right? Because in base 2 or in any other base, when yi is greater than xi, you end up with a borrow right away. Okay? But the second reason is we look at qi, which is the partial difference in this case between xi, yi, and then there's a ti, which is contributed by the column I minus 1. But if qi is less than qi, that's the other reason to give you a carry of 1 as well. Okay? So in arithmetics, we just use a regular plus or addition because that's how we do things. But if we want to convert all of this into binary or Boolean operations, then we don't have an arithmetic plus anymore. Well, we kind of do because we know how to add numbers already, but we would like to avoid that if we don't have to, right? So the question is, should we use a plus in the arithmetic sense, or should we use a or in the logical sense? So that was the last discussion from Thursday last week. You guys remember that discussion? Okay. So the biggest question really is, if one side is a 1, what can we say about the other side? That is the question. Okay. So let me give you this scenario. Let's say b of xiyi is a 1 already. Okay. What can make that happen? In other words, have I locked in the values of xi, yi if I can tell you that the borrow function applied to xi, yi is returning a 1? The answer is yes. Okay. Um, it is not shown here, but the borrow function, well, it is actually shown here, but it's not obvious. But what is the borrow function? The borrow function expressed in Boolean operations is what? B of xy is what? Not x and y. Okay, we actually see it down here. That's the not so obvious way of finding it. So we have not x and y, right? So if not x and y is a 1, what does that tell you about x and y? X is a 0 and y has to be a 1. That's the only time you can make not x and y, the whole expression, to be a 1. Okay, so that means if the left-hand side of this addition is a 1, that guarantees that xi is a 0, yi is a 1. What about qi? Does qi depend directly on x and y?
Yes.
It does, okay? It is, in short, it is the exclusive or between x and y, right? So without using the long, not and or expression and just looking at as exclusive or, what is 0 exclusive or 1? It's 1. So that means qi is guaranteed to be a 1 if bxiyi is a 1. Is that okay? But if qi is a 1, what does that tell you about b of qiti? It has to be a 0. Okay, now you can tell it has to be a 0 from two perspectives. One, you can tell it from the perspective of just arithmetics. Because qi is a 1 already, ti can be a 0 or a 1 because we're talking about binary numbers. 1 minus 1 has no borrow, or has a borrow of 0. 1 minus 0 also has a borrow of 0. So once we know that qi is a 1, this b function is not going to give us a 1. It's going to give us a 0. Is that making any sense? Okay. So that means, oh, well, that's kind of neat because that means only up to one side of these two, of the plus, can be a 1. They cannot both be 1s at the same time. Well, guess what? The only time the or versus the plus makes a difference is when both sides are 1s. And that is not happening. So that means, go ahead.
So we can use or.
We can, in fact, use or in place of addition, which is great because that's a Boolean operation. It's just a simple gate. And in fact, it is great in another way. Didn't we go through something, a reasoning like this for addition and how, the two carry can be combined using an or for the next column? So it looks like the structure of a subtractor looks exactly like the structure of an adder with some minor differences. Is that okay? All right. So we're going to move on and talk about, can we then make use of the look ahead mechanism that we have already talked about for adders? Just so that we understand why we talk about this. Why do we look into the carry look ahead mechanism for adders? So kind of go back in time a little bit and think about the rationale, not exactly the details, but the rationale of a carry look ahead adder as opposed to a carry ripple adder. Why do we look into carry look ahead? Yes.
It makes the additions faster. Well, not necessarily faster, but it doesn't matter how many bits.
Exactly.
It takes the same amount of time to.
It does make it faster. In fact, it makes it way faster. The more bits you have, the wider the adder, the more speed up you're looking at, the speed up factor you're looking at. And that has to do with the carry look-ahead mechanism, guarantees that you can get to the carry bits within 3 propagational delays. Okay, it doesn't matter how wide your adder is. Your adder can be 8-bit wide, it can be 64-bit wide, but in theory, it will only take 3 propagational delays from the time you have the x and the y's determined to the time you have all the k terms determined. But if you use the carry ripple method, then it will take 64 times, whatever propagational delay you need for each full adder, which is already at least 2 gate levels. Is that making any sense? Okay. So we would like to see whether that logic, or whether we can make a subtractor also to use that trick. So I just zoomed out to look at the rationale of something, and now we are zooming back in and say, well, can we work that out so that we can apply that same method for subtraction? Is that okay? Is this all zooming in and out making anyone, wanting to throw up? No? Okay. You know how those, amateur, videographer, they like to zoom a lot and make it fast, zoom in, zoom out, and then they pan while zoomed in, right? So that makes people nauseate because, then you have motion sickness just looking at the screen. So I hope I'm not doing the same thing. All right, so what we'll do is we're going to look at this long derivation here, but not the details, okay? So we'll get back to the details later. All we want to do is to focus on, this is ti plus 1, which is the borrow bit of column I plus 1, and it can be expressed like this, okay? We'll ignore the derivation for the time being. We'll get back to it when we have time, okay? Does this look familiar or vaguely familiar? Okay, it looks like something that we have seen before, but not exactly the same as what we have seen before, right? Because in addition, it would be xi and yi without this negation in front of the xi. And it would also be xi or yi without the negation in front of the xi. That's what we had for addition. This is for subtraction. Is that okay? So what I'll do next is to look at this and go like, I'm going to redefine P and G terms. So you can actually see how, in here, I use underline, with the RE to emphasize that G and P are in fact defined differently when we are dealing with a subtractor, even though I reuse the same letters, okay? But you can see that, oh, okay, it's very similar to how we defined G of I for adders. It's just that we put a negation symbol in front of xi. Okay. Doesn't seem to be very different, just a little bit. And pi is kind of the same thing. Okay, with this pi definition, we just have an extra negation in front of xi, but everything else seems to be pretty much the same as what we had for adders. Is that okay? So the next step is very simple, and yet it is almost magical, okay? So the next thing we do is we look at this expression, okay, the last line over here, and then we look at how gi and pi are defined, and then we express ti plus 1 using the new definition of G, the new definition of P, and Ti. Does that look familiar to you? If it does not, it's time to do some studying. And I'm not kidding. Okay? It should look familiar to you, because this is exactly what we had for adders, except the T was a K, and that was it. K of I plus 1 is Gi plus Pi Ki for an adder. This is what it looks like for a subtractor. Now, why is this such a great thing to have? Why is this particular step going from all the way from the beginning to here, why is this magical? Well, it is almost magical. I have to say it's almost magical because I do not believe in unicorns. Except when I watch party squatty advertisements. Now those unicorns are funny. Now you guys were wondering, what is that? What is he talking about? Do that search on your own after class, okay? And you may not want to have a big meal, right before watching that either. Okay, so anyhow, using this, we can actually expand t of 1 the same way as we expanded k of 1. We can expand t of 2 just like the way we expanded k2. T3 is almost the same as k3. And with every single one of those expansion, what is the difference? The letter t and the letter k are exchanged. But structurally speaking, they are exactly the same. So that means in general, if we want to find out what is t n plus 1, does this look familiar to you? It should, okay? Because we talked about this on last Tuesday, 1 week from today. Except in that case, the T0 was a K0 to refer to the carry bit input. Now we are referring to the borrow bit as an input. But structurally speaking, they're exactly the same. So what is the big deal? Okay, why is this so great? Well, there are a few reasons. One, we can reuse the same trick that we had for adders. So now we know that, for subtraction, we can do everything in 3.5 gates. I said 3.5 because there's this extra negation in front of pi. Is that okay? But that's really neat. But there's one more advantage to the whole thing. We can save a lot of silicon because we don't need the silicon for an adder on top of the silicon of a subtractor. We can have a unified structure for both adding and subtracting. Okay? Because the complexity coming out of this thing here really has to do with how the P and the G terms are conjunctioned, and then how the result of the conjunctions were put into a disjunction gate. That is the complexity coming out of this. The complexity doesn't come from the fact that, oh, we have a negation in front of xi for gi over here, and we have a negation of xi in front of xi for pi. That is not any complexity at all. So if the adder and the subtractor share the same complex structure, we can now reuse that structure. If we need to add, we take out the negation. If we need to subtract, we put in that negation. So we can unify the design and have one single piece of hardware to do both adding and subtracting. It's just that we have one bit to specify, are we adding or are we subtracting? If we're adding, we do not negate xi. If we are subtracting, we negate xi. And that is easy to do. Okay? So do we have any questions up to this point? Because up to this point, if we zoom all the way out to the forest, okay, what we have seen up to this point are transistors, okay? Things that we can actually buy and physical quantities that we can actually measure using a voltmeter. We use those to construct a NAND gate, okay, which is a very weird Boolean operator, but nonetheless, it is a Boolean operator. And then from that, we constructed the usual negation, the usual conjunction, and the usual disjunction operators, what we know as not and or, okay? And then from that, we constructed an adder and a subtractor, right? So we have now the capability to make something that can compute, okay? Now we call that a computer, okay? Your cell phone is basically a computer, pretending to be a phone. Really, it's just pretending, it's not really a phone. Okay, so your cell phone is really a computer pretending to be a phone. So what do you think down at the very core of every single computer? What is the most basic computation operation that it can perform? addition and subtraction. That's everything boils down to addition and subtraction. Then you might think, what about division? What about multiplication? They can be boiled down to addition and subtraction. Sine, cosine, yep.
Will we be covering multiplication and division in this course?
We can, depending on how much time we have. So if I see that we are moving, fast enough and have spare time to do it, I'm more than happy to talk about, how to construct a multiplier, a hardware multiplier, just using, adders and comparators and stuff like that, shifters for the most part. Division is actually a little bit harder in some way, because with division you need a comparator, which is basically a subtractor. Okay, but we cannot talk about it until we have talked about how to interpret the borrow flag along with some of the other flags after a subtraction. So yes, we can talk about that if we have time to do it. Okay, so do we have any questions about up to here how to construct a borrow look ahead subtractor? It's really the same thing as a carry look ahead adder, except we negate xi first. That's it. There's no other difference.
I have a question.
Yes.
Logicent have something to determine whether to use the negation, like based on whether you send it.
That's a very good question. Okay, so I'm going to show you the circuit to do it. Okay, just because I kept talking about an adder and a subtractor are really the same thing. So I'm going to show you a circuit to just do that. Okay, it's going to be a fun little circuit to do. Same question? Okay, very good. I like those questions. All right, so I'm going to create a new. Oh, this is a. The previous class asked me to show them a carry ripple adder. You guys have seen this already, okay? You already have seen this. Yeah, let me just kind of go ahead and make the another circuit. Okay, so we'll add a circuit. We'll call it. I was thinking about a long name, to negate or not to negate. Okay. Controlled negate, okay? So we have one pin to say negate or not, and then we have a bunch of input pins as the input, and then the output is either the same as the input, non-negated, or it is actually negated, okay? So let's just like writing a subroutine, we'll describe the interface first, okay? We have a 1-bit input that is labeled negate, okay? So if this pin is a 1, we do want to negate the input, and if this pin is a 0, we do not want to negate. Is that okay? All right. Now we have a multi-pin input. We can make it wide, so we will make this 4-bit wide. Okay, this is X. This is our actual input. I'll just call it X. And then we have an output pin which is only 4-bit wide. It has to have the same width as X, and we'll call this just output. So the behavior that I want is if and only if negate is a 1, the output should be the bitwise not of X. If and only if the negate pin is a 0, the output pin would be just X itself. Is that okay? I can actually describe it with text down here to describe.
Data bits on the output.
Yeah, you want 4.
Yeah, we need 4 of those, 4 bits. All right, so I'm just going to use some text down here to describe what we want to do, okay? So we say if and only if negate is 1, then output is bitwise not of X. Bitwise not is tilde. There we go. There we go. Is that okay? All right. All right. So the question is, how do we do this, right? So what you need to do is to think about, okay, so we need something so that 0 blah blah 0 is going to give us a 0. 0 blah blah 1 is going to give us a 1, right? Because we do not want to change anything when negate is a 0. But on the other hand, if negate is 1, we want 1 blah blah 0 to be a 1, right? And then we want a 1 blah blah 1 to be a 0 because we want to flip the polarity. Do we have an operator that can do that? And that's called?
NAND?
No.
Not.
No. How did we get the OR function working? Exclusive OR, because this is exactly what OR is supposed to do, right? 0, 0 as input gives us 0 as an output. 1, 0 gives us 1. 0, 1 gives us a 1. 1, 1 gives us a 0. So it really is just exclusive OR. Okay, so we know we have to pick out an exclusive OR gate now. So we get the gates and we pick out the exclusive OR. Okay, that's good. The exclusive OR is going to be 4-bit wide because we're going to do the same thing to all the bits. This is why we like multi-bit gates, because it can perform the same operation to multiple bits without having me to specify the multiple gates. Okay. We also want to limit the input to only 2 pins, okay, because we only technically have 2 inputs. And we'll make it look a little bit smaller because it doesn't need to be that big. Okay, so we know that one end of this is going to come from X. That's pretty easy. And the other end, the output, is going to go to output. Okay, that part we kind of know already. What we don't know is how do we do this, right? We want to feed this into the input of the other input pin of the exclusive OR, but it's not going to work. So the question is, what do we do? Well, what do we actually want to do is we want to say 0 exclusive OR this bit is that bit. This bit exclusive OR with this bit is that bit. This bit exclusive with this that bit is over that bit. In other words, we really just want to make copies of the negate bit. Yep. The way to do this is a splitter. But it's a very weird way to use a splitter. Yeah. I think some of you are having a pretty good idea of what I'm going to do next. It's backwards, but not only is it backwards, the way we hook up the split end is like, why would you want to do that? Doesn't it defeat the whole purpose of using a splitter? No, it does not defeat the purpose of using a splitter. That's just one way of using a splitter. So for sure, the splitter is going to have is 4-bit wide because the bit width of a splitter describes how many bits is on the merged end. Okay, so 4-bit wide makes a lot of sense. We'll also have, exactly, so we're going to have a fan out of 4 so that each split end is only responsible for 1 bit. Because that's what the input bit, the input pin is. It's just 1 bit, right? Oh, I just turned it the other way. There we go. And because the split end is and the merge end are opposite this time, we can just turn the facing to west. Okay. Nope, we want to turn it to west.
You gotta change the parent's right hand.
Yeah, but that's just specifies. So if you don't want the merge end to be on top, because this is a rotation, so if you want to apply a mirror on top of a rotation, then you can use appearance and go to right-handed or centered. Okay, there are several ways to do it. Okay, I mean it just controls how it looks. It doesn't really change the functionality, right? So this end connects here. And then the interesting part is with this end, we just connect the same pin to every split end of the so-called splitter. And that's it. That's our circuit. I mean, it really does sound and look stupid because why would you want to split a wire into 4 ends and then connect all 4 ends to the same wire? But the difference is this is a 4-bit wire, this is a 1-bit wire. That is why. Okay? If you want to turn a 1-bit wire into a 4-bit wire, and by replicating that one single wire 4 times, this is how you do it.
It's better than using 4 exclusive ORs.
I think so. It's easier to work with just a splitter and have more,
Than to waste a bunch of transistors on.
Yep. Well, besides, drawing more exclusive OR gates require a lot more wire connections compared to just that. Yeah, that is very localized and contained as well. If you have a whole bunch of exclusive OR gates, your wires are flying everywhere. So this is by far more optimal when it comes to displaying what needs to happen. But it's time to check whether it works or not, right? So we want to check to make sure that 1 is preserved. If I have a 1 in the input and the gate is 0, it is preserved in the output. Okay, that's good, right? So the next thing we need to test is, what if I change the gate from 0 to 1? Then 0, 1, 0, 0 should become 1, 0, 1, 1, right? So we want to double check. There we go. So how do we make use of this in a blah blah look ahead blah blah blah? Now I use blah blah because it can be borrow or carry, and I use blah 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 because it can be adder or subtractor.
You would put this right before your X input.
Exactly.
So
Output is your new X.
all you need to do is negate X.
Yep, because all you need to do is to control, do we want to negate X? And that turns, if negate is 0, it's an adder. If negate is a 1, it's a subtractor. But you preserve, remember the K3 that you have to do, it's look exactly the same. You don't have to redo all the complex circuits. All you have to do is to put this in front of what we used earlier as X to feed into the P and the G's. Is that okay?
I just have a question about logic. Like, did you have to make the fan out 4? Would it work the same if we did just fan out 1 and then assign all the bits to?
No, because if you turn the fan out to just 1, that 1 wire, and you assign all the bits to that 1 wire, then that 1 wire is once again a multi-bit wire. Then you would not be able to connect from a 1-bit pin to the 4-bit wire. So that's why you have to split it into individual bits first. All right. So are we good with this? Isn't that cool? You can have an adder or a subtractor, and you can flip it by 1 little bit. I think that's pretty cool. All right. So we are pretty much done with adding and subtracting. The next topic that we have.
No. I'm just sharing the next topic.
Okay. All right, so the next topic is signed value representation. Okay. And this one is an interesting topic because it is both technical in a sense, but also it's a thought exercise in another sense. Okay. So we'll just go ahead and go through the text a little bit first. A value represented by a base 10 number -45 is a quantity, and we describe that quantity as -45. That's a typical way to do it. In other words, the representation -45 is a means for communicating a quantity of, -45 as a quantity. Okay, so it's really just a notation convention that we use. Okay, we use a negative or subtraction symbol ahead of a particular quantity, and together it means that is on the negative side of the number line. Okay? So are there any questions about this convention? Nope. Okay. So we can use the same convention in base 2, but there's a little bit of a problem. Everything inside the computer are zeros and ones. So it doesn't really have a place or a means for you to say, oh, this is negated, okay, arithmetically negated. So it doesn't have a mean to do that. But then someone's going to say, well, that's pretty easy. We can just say that 0 means it is not negated and 1 means it is negated. So that means we can use 1 bit to specify which side of the number line that value belongs to, and then the rest of the bits to specify the magnitude of how far it is away from 0. Okay? That seems to be pretty logical, seems to be pretty easy. But there's only one problem with that approach. You can no longer use the same adder and the subtractor to deal with numbers that are signed. Okay? Because you have to take that sign bit, the direction bit into consideration. So, so you can do it. I mean, you can actually build some extra circuits and say, okay, if this is a negative value, we'll turn the adder into a subtractor, and then we'll flip the other bits, we'll turn off that bit. You can do that. You can do some, bitwise manipulation to make that work. But we also have a second problem. How do you represent 0? Well, now you have 2 zeros, because you have 0 as a quote-unquote positive 0, where the direction bit sets 0. But then you also have a negative 0, where the direction bit is a 1. They represent the same quantity because 0 is really 0. It doesn't matter. It doesn't have really a sign, associated with it. So we have that problem. So instead of doing all that stuff, we'll move on to section 3 now. Section 3 is talking about arithmetic negation. In other words, how do you flip the sign of a value? We don't really think about that much in base 10, because in base 10, it is just a notation thing. If you give me a value, a quantity of 45, I can apply the negation operator, and that will end up with the negative quantity of the same value. Is that okay? So I do want to emphasize, why I put parentheses around this one, because on the left-hand side of this equal, the negation or the minus symbol is an operator. It is doing something to 45. On the right-hand side, it is just a notation of the quantity is 45 to the left-hand side of 0 on the number line. Is that okay? Does everybody understand the same symbol means 2 different things on the 2 sides of the equality? One is an operator, the other one is just a notation. Are we good? Okay. So we move on to some known properties of negation as an operator. If you double negate a value, you get the value back. Are we convinced that that should work? Okay, that's just normal algebra stuff, right? Then we have this one. If you start with a value, you add the negated version of that value, the sum is going to be 0. Are we going to buy that? Okay, very good. If you have a subtraction, x minus y, it really is the same thing as x plus the negated version of y, which is actually, these two can be combined into one, but are we buying this? Yes. Okay. So what if I were to tell you I can do some bitwise operations that is equivalent to negation? That might be pretty useful. Okay. So we'll look into that later. So instead of looking at things as a number line in this class, we look at a number circle. Now, because I'm too lazy to actually use software to draw a circle and put labels on it, it's all text description here. I can draw the picture, in Zerno, and because everything is recorded, it will be a part of the recording in today's video. But you can go ahead and just draw that circle on your notes too. It doesn't take much time, because it will take me as much time as it will take you to copy that. And we're gonna start a journal here. And make it as wide as the page width can afford. Okay. So instead of drawing a number line, which I think all of you should be familiar with, we'll draw a number circle. So here's a circle. And I typically make 12 o'clock 0. Okay, so that's 0. I will give you guys a choice. Do we want to work with 3 bits or 4 bits? It simply has to do with how many divisions we have in a full circle. 4 bits means we have 16, and 3 bit means we have 8. Either one would work. So 3. Okay, so we'll choose 3, which means we have 8 sections. So do we agree that with only 3 bits, you only have 8 distinct bit patterns? Yes? You have 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. Is that okay? All right. But let's not even think about bit representation. We'll just think of this as a number line. Then it gets a little bit confusing at some time, okay? So we'll just say that for now, forget about this side of the number wheel. For now, we just look at this from a very close perspective and say that is 1, okay? Because it is to the right-hand side of this 0. So we'll assign that to be 1. Okay, if this is 1, it's natural. This is 2, 3, 4, 5, 6, and then we have 7. Okay? Is that okay? Now, because this is a number circle and we only have 3 bits, this is all we can do. Okay, we can say, we find one particular bit pattern to represent 0, the next one represents 1, but we run out of bits by the time we get to 7. 7 is the last value we can represent using 3 bits. Are we good so far? Okay. But then you say, but text, since you mentioned this is a number line, or it's just a number line, but I cut off 2 ends and then connect it together. Isn't the other way to do this is to look at, so I'm going to use red in this case. The other way is to look at this as -1, -2, -3, -4, and so on. Yes, we can certainly look at things that way too, because if you just and let me use something to block 1/2 of it. I think this is fine. So if I just block the other half of the number circle and just only focus on this part, it kind of makes sense that anything to the one number to the left hand side of 0 should be -1, right? Okay. So now we have a problem. Okay, but before we get to that problem, I'm going to use green to represent the bit patterns. Does anyone want to argue and say, I don't want to use 0, 0, 0 to represent 0? Because it seems to make sense, right? Okay. So we all buy that and say, this is 0, 0, 0, this is 0, 0, 1, this is 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally we have 1, 1, 1. So the green text is really the bit representation inside the computer. Okay, you got a bunch of gates, and the output of the gates is 1, 0, 0, 0, 0, 0, 0, 0 here, and I assign a meaning of numerical value 0 to that bit pattern. Okay, and over here I do the same thing. I look at the output of 3 gates, 0, 0, 1, and then assign a numerical value of 1 to it. In other words, the black numbers versus the red numbers are no more than interpretations of a bit pattern. Okay? All right. So that sounds really confusing then. I mean, this part is okay. From 0 to 3, everything is good because we only got one, numerical value to assign to that particular bit pattern. But what about the other side? What is 110? Is it 6 or is it -2?
Yes.
The answer is, why do you care? I mean, really, the question really is, why do you care? Because inside the computer, all this is saying is there are 3 gates, and the output of those 3 gates are 1, 1, 0 respectively. What is it representing? Well, for all we know, it can be representing pixels on the screen, right? Back in those monochrome days, we have 1 pixel that's on, 1 pixel that's on, 1 pixel that is off. So we don't know how to interpret a bit until we know what to do with it. So when the bit pattern is stored in memory or in any type of storage device, it really has no meaning. It really is just a bunch of zeros right next to each other. They have no meaning. The only time they have meanings is when you're performing some operations that requires you to interpret the bit patterns as values. Now, what scenarios are we talking about? What about adding and subtracting? Do you think in adding and subtracting we need to know what each bit pattern is representing? The answer is no. The way we constructed our adder and subtractor will work the same way whether you're dealing with the red interpretation or the black interpretation of the bits. Okay, so let's do that experiment first, okay, so that we know that, oh, it works out in both ways, okay? So we'll work this out. How about, adding -2 to -1? Would that help? Okay. All right, so I'm just going to do it. Let's see. Okay, this is how I do it. I can add a new layer. Okay, so this way I can delete the entire layer after this. Okay, so we'll go ahead and say we are adding 1, 1, 1, which in this case is interpreted -1, and 1, 1, 0, which in this case is interpreted as -2. So we do the bitwise add. Okay. Now, when you perform the bitwise add, you don't need to ask, is 1, 1, 1 representing -1 or is it representing 7? You don't ask that question because these are bitwise operators. They are logical operations. Logical operations do not care about the value, the numerical value the bits are representing. So all we do is now we say, what is 1 exclusive or 1? It is 1. 1 exclusive or 0 is 1. 1 exclusive or 1 is 0. 1 exclusive or 1 is 0. That's our R function. Okay? And then we have a assumed 0 over here. 1 exclusive or 0 is a 0. It's a 1, sorry. Yep. Okay. And then now we have to deal with the carries, right? So when we deal with the carries, we ask the question of, what is 1 and 0? It's a 0. What is 1 and 0? It is also a 0. What is 0 or 0? It's a 0. Okay? Do you notice that I am not using actual arithmetic operations? I'm translating everything to Boolean operations. Okay? So now the next question is, what is 0 exclusive or 0? It's a 0. All right, so on the last column, 1, okay, so we need to figure out whether there's a carry or not. So now we say, what is 1 and 1? It's a 1. What is 0 and 0? 0. What is 1 or 0? It's a 1. That's how we put a 1 here. I am not using the concept of borrowing or carrying. I'm only using concepts of Boolean expressions. Okay? So now I have to look at this and go like, what is 0 exclusive or 1? That's a 1. Okay? Now we do have carry for bit 3, so we'll work that out too. So the carry of bit 3 is based on what is 1 and 1? 1. What is 0 and 1? 0. What is 1 or 0? Is a 1. So that means we have an overall carry of 1. Okay. Did I refer to any arithmetic operations? Nope. That's the whole point. Okay. Your adder and your subtractor is made out of logical gates, which basically are the hardware version of Boolean operators. They do not care about values. They only want to know, is it true, is it false? Okay, I'm a Boolean expression, I'm a gate, I can give you an answer that can either be true or false. So we got to this answer without using any value interpretation. But now we look at 101 and we ask, what value is it representing?
Hold up. You just left a 1 there. You can't just ignore the borrow, carry, whatever.
There's no carry, there's no borrow. There's only and or not. So which digit are you referring to?
The extra 1.
This one here?
Carry, yeah.
It is not part of the answer. It is an overall carry, but it is not a part of the answer. Because it cannot be a part of the answer because this number circle only has 8 slots. If you include this one in, then you have implicitly said that we have a circle that has 16 slots. You cannot dynamically change the number of slots in the circle.
It's just K3, right?
That is, yeah, exactly. This is K3, which is not a part of the sum. Is that okay?
But it's
You have to
not the right
truncate it.
number.
Huh?
It's still not the right number though, because we do have the -3, but
Yeah.
there's still another bit that we're not considering.
If you remember the ripple adder, there was a K3 that wasn't included. in
Yeah,
the
I'm
final
just wondering
answer.
what are we supposed to do with K3 here?
It's just hanging around, but it's not a part of the result. We will find some way to use it later, okay? Just not now. Yep. So it is. So this bit here, K3, is hanging around. We have that result, but we are not using it in any way for now. Is that okay? Okay. Because we can only use 3 bits on any slot of this particular number circle, so we cannot, just say, oh, we have another bit now. We have bit 3 that we want to add to this whole thing. We cannot do that. Okay. But you can see how this works out, right? -1 plus -2 indeed is -3. But what you need to do is to be consistent and say, oh, we are looking at the red part of the interpretations, okay? So let's work out another one, okay? Let's try to work out what is, well, 0 plus 2. Okay, that's an easy one. So we have 0 plus 2. Oops, 0, 2. And I think this one, I'm pretty sure we don't need to go through all the actual math to do it. I'll be all convinced that the result is 0, 1, 0 with an overall carry of 0. Yes? Okay. Well, is 0 plus 2 equal to 2? Yes. Oh, so this works out for numbers that are in the red. It also works out for values that are in the black. It's kind of strange, right? What if we mix it? Okay, so we'll mix it up a little bit. So we'll say, what is 1 plus -1? Okay, so we have 1 plus -1, which is 1, 1, 1. Okay, what's going to happen? Okay, 1 exclusive for 1 is 0. 0 exclusive for 1 is 1. 0 exclusive 1 is 1. Implicit, K0 is a 0. 1 and 1 is a 1. 0 and 0 is a 0, 1 or 0 is a 1. Okay, 0 and 1 is a 0, 1 and 1 is a 1, 0 or 1 is a 1. Same thing over here, so we end up with a 1 over here. 0 exclusive or 0 is a 0, 1 exclusive or 1 is a 0, 1 exclusive or 1 is a 0. Indeed, we get 0. Oh, that works too. So this is the nice thing about assigning values to the bits in this particular way is our adder and if you want to check it out, our subtractor would actually work in all cases. You don't need any special circuit to look at this bit first and then decide whether we are adding or subtracting because it just naturally works. Is that okay?
I do have a question.
Yes.
You're using exclusive OR to evaluate the first, second, third, fourth lines, right?
Mm-hmm.
And to get the fourth line, we're using the carry function, right?
Yes.
Okay.
Well, it's using the carry, but this generates a carry, this generates a carry, and then those two carries are ORed in order to get here.
Could you say that again?
Okay, so let me try to annotate it here. Okay, 1 and 1. Can you see the yellow?
Yeah.
Okay, so 1 and 1 is 1. 0 and 0 is 0.
Okay.
We take both and we do the OR between those two. So we have 1 or 0, and that becomes the carry of 1 in the next column, which is this one here. Is that okay?
Okay.
Yep. So I just want to make sure that we are not only looking at the carry of one partial half addition. We are looking at the combination of the carries of two half additions to get to the one single carry of the next column. Is that okay? All right. Okay. So this is an interesting way of assigning values to a number circle. So if you look at this, the way we assign values now, okay, what is the largest value? If we just focus on the black portion, the numbers that are labeled, in black, what is 7? How do we come up to 7? In other words, if I increase or decrease the number of bits, what change? How do we come up with this value here? I'll call this Umax, okay, unsigned maximum. So if you look at unsigned maximum, how does it relate to the number of bits that we are given? In this case, we're given 3 bits. How does 7 relate to 3 in base 2?
Base bits plus 1.
Minus 1.
Yes.
Okay. So it is 2 to the power of the number of bits. We'll call this n minus 1. So n is number of bits. Okay. That seems pretty easy, right? I mean, so with a 32-bit number, n equals to 32. So the largest unsigned maximum value you can represent using 32 bits is 2 to the power of 32 minus 1, which is 4 billion something. Okay? Okay. What about, okay, choose a different, what about this value here? That's, oh, I take it back. Let me take that back. What about this one here? This one is, if we look at numbers as signed, meaning that they can go positive and negative, this is as negative as we want it, okay? And I will address the question of why don't we look at 0, 1, 1 as negative 5? We do not, okay? But I will address that question later. So if we look at negative 4, so now the question is, we'll say signed minimum is what? How does negative 4 have anything to do with base 2 and 3 bits? Yep,
I'm gonna say it's the negation of 2 to the power of n minus 1.
you're correct. You are absolutely correct. So this is how we come up with, I hope you guys still remember in cisp310, you have ints and you have unsigns, right? How many people have an instructor that explicitly said, this is 32-bit, this is 64-bit, blah, blah, blah. Okay, so with that, okay, you can now easily calculate with a 64-bit number, the unsigned 64-bit number can represent all the way up to 2 to the power of 64 minus 1, which is a huge number, okay, pretty big. With a 16-bit number, it will only be 2 to the power of 16 minus 1, which is 65,535 in that case. That's the largest positive value when you look at it as an unsigned number. What about signed interpretation? What if I have 16 bits, but this time I'm looking at it as a signed? So it's a signed 16-bit number. Then the most negative value you can represent is negative 2 to the power of 15 in that case, which is 32,700 and something. Is that okay? But this is the general way of you're looking at a number wheel and find out what is the largest thing it can represent, what is the smallest value it can represent. All right, so here comes the next question. Why do I stop the red labeling here instead of saying, oh, we can go even all the way around it or go at least one more? Why do you think that is the case? There are, yep, go ahead.
The one at the end shows it's signed.
Sorry?
The one in the third position shows
The most significant digit? Okay, that's a very good observation. So the observation is saying that, hey, all of those numbers that are representing negative values, they all have the most significant bit being a 1. And you are absolutely correct. That's why the most significant bit is also called the sign bit. Okay, because if it is a 1, the value it is representing is negative if you choose to look at the number as a signed number. Okay, so very good. But the second reason is we really only want to have 1/2 of the slots of a circle to represent negative values and the other half to represent non-negative values. And this way, we have exactly 1/2, right? Because we have -1, -2, -3, -4 as negative values. Then you go like, but we only have 1, 2, and 3 as non-negative. 0 is non-negative as well. Okay, so that is why we kind of divide the wheel this way. Is that okay? Cool. All right. So, but this doesn't really answer the question of negation, arithmetic negation. In other words, if I give you a particular value and I say, okay, what is the bit pattern of the negated version of this? How do we figure that out? So I want you to notice something here, okay? If you subtract the red portion from the black portion and apply that to all 4 negative values, what do you get? They all add up to, or they're all 8, right? 7 minus -1 is 8. 6 minus -2 is 8. 5 minus -3 is 8. 4 minus -4 is also 8. So that means we have an interesting way to negate a value. Okay, find out the negated version of the value. Okay. So let's go ahead and look at some math stuff here. Because what we want to do, okay, so let me switch back to the normal black here. So what we want to do is to say, given x, we want to find out what is the negated version of x. So we are basically looking at 0 minus x. Does that make sense? Okay. Would anyone argue that it really is the same thing as that? Yes? Okay. Hmm? I mean, that's just algebra. Oh, right, right. Okay. I messed up. Okay. It does not make sense. There we go. Okay, now it makes sense, right?
No, you can't just turn this.
Oh yeah, it should make sense now. Because 8 minus 8 is 0, but we have the negated x here, we have the negated x here, so they should still equal. The two sides of the equality should be the same.
Commutative property doesn't work that way.
Huh?
No, never mind. I'm just kidding.
Okay. So we are convinced? Okay. So now we take this minus 8, out here, we'll deal with it later. But the problem is, when we look at the number wheel, is 8 on the number wheel itself? Even either in black or in red? It is not. We go like, oh, that doesn't work. But 7 was, right? Okay, so we'll do it like this. 7 plus 1 minus x, the whole thing minus 8. Is that okay? All I did was to change the 8 to 7 plus 1. Is that cool? Can we represent 7 using one of the bit patterns? Yeah, we can. And we can do that with the 1 too. Okay. So we look at this, and now we say this is 7 minus x, the whole thing plus 1. And then we have this minus 8 on the outside. Would that work? I just I just reorder some of the operations, right? So now here's the magical part of this. What is 7 minus x if x is a 3-bit pattern? Okay, so let's think about it. Okay, if x is a 3-bit number, 7 minus x is the same thing as the bitwise knot of x. Hold on here, right? Hold your horses. What are we talking about here? What is the tilde symbol? What do you mean by bitwise knot of x? Well, let's figure out a few things, okay? Let's just do a few examples, okay? So we'll say, okay, we'll work out a few examples. Let's just work out what is 7 minus 3, okay? And you guys know the answer already. It's 4, right? Okay, in base 10. But we also want to work this out in base 2, okay? 7 is 1, 1, 1. 3 is 1, 1, 1 in base 2, okay? Do you guys want to go for the full long subtraction or just the kind of short version of this? Sorry? Long version? Okay, we'll go for the long version. So the long version using Boolean operations goes like this. 1 exclusive for 1 is 0. 1 exclusive for 1 is 0. 1 exclusive for 0 is 1. Okay? Borrow for bit 0 is 0 assumed. So now we have 1, not 1 and 1 is a 0. Not 0 and 0 is also a 0. 0 or 0 is 0. We have no borrow from the next digit. 0 exclusive or 0 is 0. Are we good so far? Okay. We have not 1 and 1 is a 0. Not 0 and 0 is also a 0. 0 or 0 is a 0. 0 exclusive or 0 is 0. Is that good so far? not 1 and 0 is 0. Not 1 and 0 is 0. So the borrow bit for the borrow of bit 3 is 0. 1 exclusive or 0 is 1. It got us what it should be, right? But I only used Boolean operations. But the bottom line is 111 minus 011 in base 2 is 100 in base 2. Is that okay? Does it make sense? It should, okay? So we have just worked out this side in base 2. Yeah, okay, everything works out. But what about this side here? This side says, if, okay, in this case, 011 is our x. So the question is, what is tilde 011 in base 2? Tilde 011 in base 2 is flipping all the 1s to 0s and all the 1s into 0s, right? So what do we get? 100. Oh. So a simple bitwise NOT would do the same thing as a subtraction. But it kind of makes sense because 7 is a very special number in base 2. 7 as a quantity is 111 in base 2. 15 is special in the same way because 15 is 1111 in base 2. 32 is 11111. 63 is 111111. 255, sorry?
32 or 31?
Huh?
32 or
31. Did I say 32? Okay, 31, excuse me. So 31, which is 32 minus 1, is 11111. Okay? 255 is 11111111. Those are all kind of special values because they are a power of 2 minus 1. Okay? And if you subtract anything from that, you are negating the value that you're subtracting from that value. Is that okay? So are we reasonably convinced that this works? Cool? All right. So now we say, oh, so this is tilde x plus 1. Okay? Remember, tilde x is bitwise NOT of x. Okay? Bitwise NOT of x plus 1, and then we take this whole thing and then we say minus 8. Okay? Okay, so now we switch the way we look at numbers and we look at minus 8 and go, what does that mean when we are looking at a number wheel? Okay? So we scroll back up to the number wheel and we say, if we are adding, we are rotating clockwise. If we are subtracting, we are rotating counterclockwise. Does it make sense? Okay, so just imagine that you have a pointer that can rotate. So the wheel itself does not rotate. This is not wheel of fortune, where the wheel itself rotates. This is where you have a pointer that rotates. Okay, so it's more like a clock. Okay, the hand can rotate. So if addition is rotating the hand clockwise, then subtraction is rotating the hand counterclockwise. Does it make sense? So what does minus 8 mean when I have a particular value here and I say, okay, tell me what is this value minus 8? Rotate counterclockwise 8 times. Does it, right? Okay. So we go like 1, 2, 3, 4, 5, 6, 7, 8. I'm done. What do we get? The same thing. Okay? And the reason why we got back to the same place is because 8 is 2 to the power of 3. We only got 8 slots here. So if you rotate in any direction by any multiple of 8, you end up at exactly the same place as you were. Is that okay? This is modulo math, but I'm not using the math terms to explain it. Okay. So what is the how does this help us, right? We just say that drop it. Because -8 doesn't do a single thing. If you're only living on a number wheel, but not a number line, and the number wheel is a number wheel that only has 8 slots, then any addition or subtraction of multiples of 8 doesn't do a single thing. Yes?
Doesn't it still produce a borrow though?
No. Because this is it's dropped out because we are just rotating. Yep.
So it's like a tilde 0?
It is not the same thing as a tilde. A tilde 0 would give you 7 in this case, because we are locking the width of operations to 3 bits. So a 0 is actually 0, 0, 0. The bitwise NOT of 0, 0, 0 is 1, 1, 1. But we do not have a borrow because the bitwise operations is only done on this side. This is dropped out because of the way we interpret what -8 means in terms of that. Yep.
But if we were to do the math out without using the number wheel, it would make.
Correct. If we work out the actual math, then you would end up with a negative value, or you would end up with a borrow. That is correct. But we are not doing that because what we want to do is, what does negation mean when it comes to a fixed width binary number? Is that okay? So the most important part, we are running out of time, to take out of this one, if you have to remember one thing that is important out of today's class, it is this. If you are given a fixed number of bits, then the negation of a particular value is the same thing as the bitwise NOT of that particular value plus 1. Let's check. Can we do all this using logic gates? Can this be done using logic gates tilde x? That's just a multi-bit NOT gate. Okay? Can we plus 1? Yep, we got an adder, so we just need to use an adder to add 1 to the result of the bitwise NOT. In other words, so that means we can now use logic gates to perform what we know as arithmetic negation. Is that okay? We are running out of time. We will transition to the lab, but on your own, okay, before Thursday, if you want to check out this thing, you can try this out and see if you double negate something, do you get the original thing back? Check it, okay? If you add x to the negated version using this to itself, do you get 0? If you have x minus y and you translate it to x, translate that to x plus this version of the y, do you get the difference? Okay? In other words, asking you to try to use this operation as if it is negation and see if it has all the same properties as arithmetic negation. Okay? So doing that will help you understand the concept a little bit better. And because you're practicing and doing it, you will also get some experience of working with other bitwise operators like negation and just simple addition in base 2. So that's kind of the graded assignment for you, along with reading ahead of me for Thursday. So we do have a lab today, and I will transition to the lab as soon as I'm done here. I'll see you guys over at the lab.